So now we'll just actually go through some practice questions to consolidate what we've learnt in terms of graph theory, and also just the rest of the concepts covered throughout the lecture. So let's get started with the questions. So the first question, consider the following graph. Which one of the following statements is not true for this graph? Okay, so what do we have here? We just have sort of like a basic sort of connected graph. Let's read the options that are given. So this graph has 7 vertices. Let's count them. 1, 2, 3, 4, 5, 6, 7. That is true. And we're trying to find the not true statement. So A is not the answer. There are no isolated vertices. That is actually true. So remember, isolated vertices are vertices that are not connected to any other vertices by edges. As in the name suggests, they're basically isolated. And we have none of them here. All vertices have an even degree. Okay, let's have a look at that. So this has a degree of 2. Remember, degree is the number of sort of connections that a particular vertex has with other vertices or to itself. Basically the number of lines or edges going off of it. That's the way I like to think of it. So this has a degree of 2, 2, 2, 4, 2, 2, 2. So all of them are even. So that's true. 6 of the vertices have the same degree. Yep, 2, 2, 2, 2, 2, 2. Yep, 6 of them have the same degree of 2. The sum of the degrees of the vertices is 14. Okay, let's count them. So 2, 4, 6, plus 4, 10, 12, 14, 16. Yep, so that's our answer. The sum is actually 16, it's not 14. The adjacency matrix for the graph above with nodes as labeled is, okay, so we are trying to work out the adjacency matrix for this graph. Remember, adjacency matrix is basically a matrix representation of a graph. And the way that we sort of look at it is we assign the rows and the columns with numbers. So they haven't labeled it for us. I'm just going to label one of them just so everyone knows what's going on. So we have 1, 2, 3, and 4. And basically, we're just looking at the connections and seeing whether, how many connections there are, whether they are correct. So let's just pick a random sort of vertex. So let's just pick this vertex over here, which is vertex 1. It has connections to vertex 2, one connection to vertex 2. So in the intersection between 1 and 2, there should be a 1. And there's not a 1 here. So therefore, C is actually not the right answer. So we need to have a 1 here at the intersection of 1 and 2, because 1 and 2 have one edge that is connecting them. So if there is a 0 in that spot, it's not the right answer. Yep, so we want a 1 here and a 1 here. So it's either A or B. Let's just pick another random point. So okay, let's actually look at the difference between these two answer options. And the difference lies over here, between 1 and 1 in itself. So is there any loops here for 1? And the answer is no. We don't have any loops. We don't have any edges that just connect 1 to itself. Because we have 1 connecting to 2, 1 connecting to 4, and 1 connecting to 4. So there shouldn't actually be a 1 here. So therefore our correct answer is actually B, in terms of finding the adjacency matrix. I hope that makes sense. Let's move on. Okay, consider the following graph. The adjacency matrix for this graph with some elements missing is shown below. Okay, this adjacency matrix contains 16 elements when complete. Of the 12 missing elements, and then we're just sort of filling the blank type of thing. So let's just actually fill out the adjacency matrix before we go on to find the correct answer. That's probably the best method of doing it. So we're trying to find what goes here, and remember, looking at the intersection point. So X and W. So we're looking at how many connections there are between X and W. So there's actually 1, and we're looking at direct connections only. Because obviously there are second degree connections as well. So you could do, y, x. We're not looking at those. We're just looking at direct edge connections. Oops. So we have 1 and 2 connections between W and X. So there should be a 2 here. Next, looking at this one, which is W and Y, we have, again, 1 and 2 connections between W and Y. So 2 goes here. And next, looking at W and Z. W and Z. Well, there is just 1 connection. So we can just write it there. And the thing about adjacency matrix, the rows are actually the exact same as the columns. So this is actually also going to be 2, 2, 1, because now it's just, sort of flipped. It's the exact same thing. Okay, now let's move on to the X row. So looking at the connections with X. So X has, and if you want to tell if you've done it correctly, just look at how many edges are going off of, a particular vertex. We have 1, 2, 3, 4, 5, 6, 7. And if this equals to 7, then we have done it correctly. 1, 2, 3, 4, 5. Oh, sorry, just realized this is the same edge. It's a loop. So 1, 2, yep, so it should just be 6, not 7. My bad. Okay, next looking at X. So X has 1 connection to Y and 1 connection to Z. Pretty straightforward. So we also fill out the vertical as well. So 2, 0, 1, 1. Next, looking at Y. So Y and Z. Y and Z, only 1 connection. Like so. And Y and Z, 1 connection. And then we're done. So that's all we had to do in this case. So the adjacency matrix, so of the 12 missing elements, 8 are 1 and 4 are 2. So we have 1, 2, 3, 4 2s and 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9 1s. So it's not A. 4 are 1 and 8 are 2. 6 are 1 and 6 are 2. 4 are 0. 4 are 1 and 4 are 2. So we already know that we have 4 2s. So we can already cancel our stuff where it's more than 4 2s. We cancel out this. So out of these 2, sorry, I think I miscounted. Oh, sorry, I counted this one as well. So it should just be 1, 2, 3, 4, 5, 6, 7, 8. Oh yeah, so that one's actually correct. I think I miscounted that one before. Just rub that out. Okay, let's move on. Again, if you have any questions whatsoever, just pop them into the chat and I'll be monitoring the chat, so I'll answer them as the questions come in. Okay, Euler's formula relating vertices, faces, and edges does not apply to which one of the following? So, Euler's formula, does anyone remember what that was? So if you do, pop it into the chat. But going back a few slides, Euler's formula is the formula where we basically have a planar graph and we're using the Euler's formula just to prove that it is a planar graph. But if something we know is a planar graph, we can also use it to find the missing number of vertices, the missing number of faces, the missing number of edges. So just quickly recalling what the Euler's formula was, it was vertices plus faces minus edges equals to equals to 2. That's basically the Euler's formula. So if you have, one thing missing, for example, you don't know the number of edges, you can use the number of vertices, faces, and this formula to work out the number of edges. That can work for, any one of these. But this question, what we are actually doing is seeing which one does it not apply to. So basically, we're trying to work out which graph is not planar. Remember, Euler formula only applies to graphs that are planar. And how can we determine that? Well, we can determine if a graph is planar if we can basically draw an isomorphic graph for a particular, a graph that does not look planar. And sorry, just to recall, planar means that we have no edges that are intersecting each other at points that are not vertices. So for example here, currently this graph does not look planar. But if we redraw this edge, so get rid of this edge and redraw it, now that it's planar, we have nothing that's that is intersecting other vertex edges. What about this one over here? Can we redraw it? A little bit difficult to see here, but basically what we can do is move this vertex over here, and that basically solves the problem. And then we'll have this, this, and this. And that basically solves the entire problem. What about this one over here? What's intersecting? Oh yeah. Basically this one is intersecting with this one and this one. Okay, so there's a really easy solution for this one as well. Basically what we can do is move, this vertex outside over here. And then we can draw connections to it like this, like this, like this. 2, 3, 4, and like this. That way we have no intersections, and that's all fixed up. So that's also planar. This is planar. This is planar. What about this one? This one is also planar because basically what we can do is just redraw this edge like this. Redraw this edge like this, and basically we've solved the issue there. So this one's planar as well. This one, you can already tell it's sort of not planar. It's really difficult to redraw because we can redraw this edge, for example, like this, no problem. What else is intersecting? This one we can redraw like this, no problem. Now, when it comes to redrawing this edge over here, if we had to redraw like this, now the edges are intersecting. So there's actually no way of redrawing this graph to make it planar. So therefore, this is our correct answer. So in this question, the examiner's being really indirect, or your teacher, whatever. So if you get a question like this, although it's technically asking for Euler's formula, what it is actually assessing is your ability to draw isomorphic graphs, your ability to understand what the Euler formula can be applied to, which is planar graphs, and also your ability to recognize planar graphs. So testing a variety of skills here, but in a sort of an indirect way. Okay, bus routes connect 6 towns. The towns are North End, Opera, Palmer, Quigley, Rosebush, and Seatown. The graph below gives the cost in dollars of bus travel along these routes. Bai lives in North End, and he will travel by bus to take a holiday in Seatown. Euler's formula V plus F equals E plus 2 holds for this graph. Complete the following by writing the appropriate number in the boxes provided below. So this is a pretty straightforward question. We know the Euler's formula, we're just applying it to this question and just showing the examiner we know what a vertex is, we know what a face is, we know what an edge is. So first of all, how many vertices are there? So there's 1, 2, 3, 4, 5, 6 vertices. What about the number of faces? Well, remember, faces are the enclosed regions between edges and vertices. So we have 1, 2, 3, 4, 5, 6, and we also count the outside region as a face, so 7 faces. What about the number of edges? There is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 edges. So that all makes sense. That cancels out. So we know that we've done everything correctly. Okay, next question. Which one of the following, and also while I'm doing these questions, if you're watching this lecture live or you're watching the recording, please make sure to actually pause when I get to a particular question, attempt it yourself, and then watch the solution. Because specialist maths is a subject that requires you to have a lot of practice, so really start to get all your practice in, from the beginning. Don't wait till, it's exam time or SAC time. Okay, which one of the following graphs contains an Euler circuit? So, when did we say an Eulerian or an Euler circuit existed? Well, we said that an Eulerian circuit only existed if all of the vertices had an even degree. So we're just basically trying to find out the graph that has all edges being of even degree. So A, we can clearly cancel out because this one has a degree of 1, which is odd. This vertex has a degree of 3, so we can cancel that one out. This one looks correct. Oh, never mind. This one has a degree... Oh, sorry, never mind. It does have a degree of 4. I thought this was just these 3. Anyways, this one looks to be the correct answer. But let's look at the other ones. Oh, this one has a degree of 3. Not the right answer. And this also has a degree of 3, so not the right answer. So indeed, our answer is C. Oops. Okay, moving on. Here we have a short answer question. Aiden, Braden, Carey, and Dunlop, Edwin, and Farnham are 6 towns. The network, or the graph, shows the road connections and distance between these towns in kilometers. How many different ways are there to travel from Farnham, to Carey without passing through any town more than once? Okay, so what we are trying to do is find a route from Farnham, which is over here, to Carey without passing through any town more than once. This one sort of trial and error, I would say, just like, work out all the different ways and just sort of figure it out. So the first way is 1, 2, like that. Then we also have 1, 2, 3. That's another way. What about 1, 2, 3, 4? That's another way. So currently we have 3. Next we have 1, 2, 3, without passing through any town more than once. Oh, okay, so we can't pass through any towns more than once. That's all good. I was just checking this one. Oh yeah, that one's good. This one. Okay, so we have 4 in total. So the first one is like this. Second one is like this. Third one is like this. And the fourth one is like this. So 4 in total. Yeah, I can't see any other ones. If you have spotted another one, just let me know in the chat. Okay. An engineer plans to inspect all the roads in this network. He will start at Dunlop and inspect each road only once. At which town will the inspection finish? Okay, so start at Dunlop and inspect each road only once. So he's visiting every single edge exactly once. And we're trying to work out which town will this inspection finish. So what is this? This is actually an Eulerian trail, if you think about it, because you're passing through every single edge. You're not repeating any edges. You can repeat vertices, doesn't matter, but you're not repeating any edges. And you're starting from one point and ending at another. So it's an Eulerian trail. And remember, an Eulerian trail starts at one vertex, which has an odd degree, and ends at the other vertex, which has an odd degree. So Dunlop has an odd degree. So what's the other vertex that has an odd degree? Well, it's this one over here, Breeden. So that is where he will be finishing off. And obviously you can do a bit of trial and error, but this is the best method. For Eulerian trails, you start at one odd vertex and end at the other odd vertex. So that's why we need two odd vertices for a Eulerian trail to exist. But for Eulerian circuits, it needs to be all even degree. Okay, another engineer decides to start and finish her road inspection at Dunlop. Okay, if an assistant inspects two of the roads, this engineer can inspect the remaining 6 roads and visit each of the other 5 towns only once. How many kilometers of road will the assistant need to inspect? Okay, let's see. Another engineer decides to start and finish her road inspection at Dunlop. If an assistant inspects 2 of the roads, this engineer can inspect the remaining 6 roads and visit each of the other 5 towns only once. Okay, so again, we're starting and ending off at Breeden, but this time we're not visiting all the other vertices. So the main sort of way that I can think about it is, sorry, let me just read this one again. If an assistant inspects 2 of the roads, this engineer can inspect the remaining 6 roads and visit each of the other 5 towns only once. How many kilometers of road will the assistant need to inspect? Okay, so it doesn't give us any indication on whether the other engineer needs to start or end at a particular spot. It just says that it's going to inspect 2 of the roads. And the engineer will inspect the other 6 roads, starting and ending at Dunlop. So what are the ways in which we can visit 6 vertices starting and ending at Dunlop? Well, we can go like this, like this, like this, and this. So what is that? 1, 2, 3, 4, 5, 6 roads. That's probably the only way in which we can do this. Otherwise, we can do, like this. 1, 2, 3, 4, 5. That's 5. 1, 2, 3, 4, 5. Again, doesn't work. So this is the only possible way. So therefore, the 2 that the assistant will inspecting will be these 2 over here. So this one and this one. So just totaling it up, it will be 240 kilometers. Okay, let's move along. Again, if you have any questions, please pop them into the chat. Okay, water will be pumped from a dam to 8 locations on a farm. The pump and the 8 locations, including the house, are shown as vertices in the network diagram below. The numbers on the edges joining the vertices give the shortest distance in meters between locations. Okay, question AI. How many vertices on the network diagram have an odd degree? This one's a bit of an, just a basic question, just counting the number of vertices with an odd degree. So this one, even, has a degree of 2. This one, 1, 2, 3, 4, even, 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 1, 2, 3, 4, 5. Oh, okay, this one's odd. 1, 2, 3, 4, 5. This one's odd. 4, even, and even. So, 2 vertices. The total length of all the edges in the network is 1,180 meters. A journey starts and finishes at the house and travels along every edge in the network. Determine the shortest distance traveled. Okay, so we're starting and ending at the house. So basically what we are doing is sort of like an Eulerian trail where we go, across through all the edges, and then there's one that we need to repeat. Which one will that be? So if you think about it, what is an Eulerian trail? An Eulerian trail is one that starts at one odd vertex and ends at the other one and visits every single edge exactly once. So therefore, in this case, if we are trying to visit every single edge, but then we will, so let's say we start at the house, we will end at this one, and we would have traveled 1,180 meters. But we also need to come back to house. So therefore, we'll need to travel on this edge one more time. So therefore, the distance that it will travel will be 1,180. So that's the total distance of all the edges combined, plus that extra 70 just to get to home base. So therefore, our answer here will be 1,250. Yep. Okay. IV, a Hamiltonian path beginning at the house is determined for this network. How many edges does this path involve? What is a Hamiltonian path? Well, a Hamiltonian path is basically something that's going to visit every single vertex exactly once. So what could be a possible one? Let's just have a think about that one. So let's just say we are starting at the house and we need to visit every single vertex. So we need to go to this one, 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 this one. Okay, so that's basically the Hamiltonian path. We visited every single vertex. So what is that? What is the number of edges here? So it's 1, 2, 3, 4, 5, 6, 7, 8. So regardless of how you actually do this question, you know, your path might look a bit different. The ultimate answer that you're going to get is going to be 8. Okay. This question over here. Maggie's house has 5 rooms, A, B, C, D, and E, and 8 doors. The floor plan of these rooms and doors is shown below. The outside area F is shown shaded on the floor plan. The floor plan is represented by the graph below. On this graph, vertices represent the rooms and the outside edges represent direct access to the rooms through the doors. One edge is missing from the graph. Okay, so question C. Maggie hires a cleaner to clean the house. It is possible for the cleaner to enter the house from the outside area F and walk through each room only once, cleaning each room as he goes and finishing in the outside area. Complete the following to show one possible route that the cleaner could take. So he's visiting every single vertex exactly once. Really important to notice whether we're visiting every single edge or every single vertex. In this case, it's just rooms, so every single vertex. So using this network over here, what's the route that he could take? And what we are trying to actually find in this case is a Hamiltonian cycle. Starting off at F, we can go A, B, E, D, C, and F. So that's a possible route. There's possibly other ones as well, but this is the one that I can immediately think of. Usually for these types of questions, there are multiple answers. So if you write it the other way around, that's fine as well. A, B, then E, then D, and C, and then finally F. What is a mathematical term for such a journey? We just mentioned this. It's a Hamiltonian path. So I'm not going to write it down, but it's a Hamiltonian path. And really important to recognize that it's a Hamiltonian cycle, not an Eulerian circuit. We are visiting every single vertex, not every single edge. Okay, and we just have one last question before we end the lecture. Consider the following graph the smallest number of edges that need to be added to make this a connected graph is. Okay, So we are basically trying to work out how many edges we need to add to make this a connected graph. Remember, a connected graph, the number of edges, oops, that's not an E, is equal to the number of vertices minus 1. So how many vertices do we have? 1, 2, 3, 4, 5, 6, 7. So therefore, the number of edges that we need is 7 minus 1, which is 6. And we already have 2, so we already have 3. So we just need the remainder, which is 3. So that's the answer there.